We are ready to begin. Please recording. Okay.
Yeah.
Okay. So it is an honor for myself to present to Professor John Erik Fornæss, who today is going to give us the conference, Henkin Ramirez Kernels.
Oh.
So Professor Fornæss, whenever you want to begin.
Okay, yes, thank you very much. I don't wonder if I messed up this. Oh no, I think maybe it's okay. Okay, so I'm very happy to for the invitation to participate in this tribute to Ramirez's to celebrate his career. So my talk is about Henkin Ramirez kernels, and they worked in the strongly pseudoconvex case at first. So I will talk reproducing kernels in the weakly pseudoconvex case. So I cannot mention all the literature. So just some things. So the first, this is the table of contents. I will talk about the support surfaces, which are hypersurfaces tangent to the outside, tangent to a domain, but like living in the outside. And then some small calculation, which is basically the only technical thing I will do, a very short calculation. And I will do it maybe a little bit later in slightly more complicated, but very, very simple. And then I will mention some thing about the Henkin Ramirez reproducing kernel and go to the weakly pseudoconvex case. The first case is the Kohn-Nirenberg example, which caused a lot of problems for us. And then I move to the convex case, and in particular on some work with Diedrich and Wiegerink on ellipsoids. And then I will talk about more general domains of finite type, and then linearly convex domains of finite type. Then I will go back to actually Henkin Ramirez reproducing kernels for a special domain in C2, the Kohn-Nirenberg domain that I mentioned earlier. And then some concluding remarks. Okay. So the support surfaces, I have a pen, maybe it works. If there are support surfaces, or if you have a theta in the boundary, the support surfaces are supposed to be lying outside the domain. And they are given by some function phi on theta z from the boundary across a neighborhood of omega bar, and which is smooth and holomorphic in the second variable. And we can write also that phi index theta of z is this function phi of z theta. And then the sigma thetas are those supporting hypersurfaces where the phi theta is 0. And they only touch the domain at this point. And this can be done locally for strongly pseudoconvex domains and gives you a locally defined phi. And from then you can use d-bar Hermanders, d-bar techniques to get globally defined phis. And these estimates do not depend on subnorm estimates. And then Henkin and Ramirez used this, satisfying some optimal estimates on as far as tangency, namely that the real part of this function, which vanishes on sigma of theta, at least vanishes second order if z is in the closure of the domain. These support surfaces are important in the integral formulas that appear, because 1 over phi, the function 1 over phi, is the bad guy in these kernels, in these integral formulas. 1 over phi appears, and if phi is very close to 0, this causes big problems. So we need to be as far away from zero as possible. So it's important to have as much control as possible on how close fees to zero are inside the domain, the closure. And now I mentioned a key difficulty in which I will be using later in the talk. Namely, you take the simplest possible example. It looks like omega is sort of like a ball, but you notice that z is x plus iy, w is u plus iv, but the y does not appear in this formula. So that is the key difficulty, that y is not present. The natural phi for zeta equals 0 in the origin is you can just use the complex tangent plane, which is given by w equals 0. The w equals 0 is the complex tangent plane. But w equals 0 is very bad because then phi equals 0 is, which is the w equals 0, includes the y-axis, which lies in the boundary. So phi vanishes identically on the boundary. And that means that the function 1 over phi is way too large. In fact, there's no conversions in the integrals that are being used. So it's terrible. And this is overcome by a trick. And this will appear in various versions later. You take this term x squared. So you remember that y squared is missing. Y squared is split it into sum of two parts by adding and subtracting y squared. Then you can rewrite it as the half times the norm of z and half times the real part of z. And then you can write the domain by replacing x squared by this new expression. So r becomes this. And u is the real part of w. So all in all, you write the defining function r as the real part of some holomorphic function plus v squared, and now you have plus z squared. So x squared plus y squared now appears. So now we change coordinates. We write with the prime coordinates. You have the z prime and the w prime. And the w prime is what's inside the real part there. So then we get r is the real part of w prime plus y prime squared plus z prime squared. And the only difference from the previous case is that this has become z squared instead of x squared. So it becomes tangent in all directions. And this is the optimal kind of tangency you can have. So this is a very key calculation. Okay, so now the Henkin Ramirez reproducing kernel was handling the strongest pseudoconvex case. So let me just recall the definition of this business. So the definition of pseudoconvex domain. Oh no, what happened? Okay, I'm back, I guess. So the definition of pseudoconvex domain is that if you take a complex tangent vector, then it's given by, if the domain is given by some defining function r less than 0, the complex tangent space is given by some formula like this. And the Levy form is something looking like somehow Hessian, real Hessian, sort of like, and it calculates the second derivatives in the direction of this tangent direction. And the strongest pseudoconvex domains that Henkin and Ramirez were working on were the ones where this Levy form is strictly positive. And once you had these strongest pseudoconvex domains, Henkin and Ramirez found this holomorphic reproducing kernel, and it uses this phi as the major building block, the support surfaces as a major building block. And this generalizes the classical Cauchy integral formula in one variable. F of z is 1 over 2 pi I, integral over the boundary, f of zeta over zeta minus z, the zeta, for one complex variable, and phi in this case is just zeta minus c. So it's singular, but not too singular. Okay. And now the weakly pseudoconvex case. How to handle the more general weakly pseudoconvex case. So the weakly pseudoconvex domains are those for which the Levy form is non-negative. It can be 0 in some directions. And among weakly pseudoconvex domains, you have the infinitely flat ones. Those are very difficult to analyze. And not so much has been done actually with those. Although I have to say, well, Joe Cohn has proved some important theorems. But from this point of view of representing kernels, reproducing kernels, they are really difficult. And there's an intermediary case that are those of finite type. So let me recall that. If you have P in the boundary of omega, then you can have some kind of complex curve, gamma. Well, it could be that it goes inside. And you can define how much the order of tangency T of P gamma with the boundary at P. You can measure this. And then we say that omega is of finite type if there is a uniform upper bound on this type, order of tangency, when P varies over the boundary, and gamma could be any point, any curve through P. And yeah, so this is, yeah, so this is, so yeah, so finite type if there is a uniform bound on how large these numbers can be. And this is goes back to John D'Angelo. He introduced this very, very important notion. There are other finite type conditions also, but this one turns out to be the really important one. Okay, so the Kohn-Nirenberg example is there is a serious difficulty in carrying the Henkin Ramirez reproducing kernel over to weakly pseudoconvex case, which was discovered by Kohn and Nirenberg in this paper, a pseudoconvex domain not admitting a holomorphic support function. So in other words, this picture of having a point and having a support surface like this staying outside was thus not possible. Any support surface, anything you try has to enter the domain. And the set, if this is phi, the set where phi equals 0, then 1 over phi is just a terrible disaster there. So you can forget it. I made a small adjustment to the Kohn-Nirenberg example. It's not important, but I thought it was fun because it was degree 6 and they had used degree 8. And for degree 4, it turns out there is no way you can have such a phenomenon. But anyway, so these domains are written like this. You have the real part, omega t, the real part of the second coordinate plus something to make it bounded, plus e to the 6, and then the real part was e to the 4th times c squared. So it's homogeneous of degree 6. And for this to work, t has to lie between two numbers, 1 and 9 over 5. And then they are pseudoconvex. But these curves that you try to make through the origin, which is on the boundary, just have to enter the domain. They cannot lie outside. Not possible. So there is no smooth family phi of zeta c of support surfaces as was used by Henkin and Ramirez in the reproducing kernel in the strongly pseudoconvex case. So this means that people started thinking about maybe to avoid the Nirenberg difficulty, you take the convex case, the ordinary convex case. Because at least for the convex case, you have at least a complex tangent line, if nothing else, which stays outside. So the function's phi can be written down using the complex tangent lines, the tangent space. But to get the Henkin Ramirez reproducing kernels, these are not good enough in general. And because, as I said, if the tangency is too high, then the 1 over phi becomes a big problem in the kernel. So that's the question then, what to do. So here is one paper that I wrote with Diederich and Wigerink on ellipsoids, sort of flattened ellipsoid, I guess one should say. So in other words, you have simple convex domains of finite type that are given by a sum of powers of the coordinates less than 1. The ordinary ellipse would be, well, yeah, then this is a sort of, if you have, the numbers are 2, then you have the ball, not an ellipse, but okay. One should maybe be more general and have a constant times the xj and the constant times the yj are different. But we didn't look at that. We were worried more about these powers. We looked at these kinds of domains, and we were not the first to do this because already 10 years earlier, the case when these are equal was done by Range in his paper on Hölder estimates for D-bar from conference in Cortona in 1977, maybe, published in 78. And so the main new difficulty is when these are different. And then you have the simplest support surfaces, phi equals 0, is given by the complex tangent plane. However, the complex tangent plane has order of tangency 2mj in the xj direction and 2mj in the y direction. So this looks a little bit similar to what I did when I said talked about the main difficulty or key difficulty. When these are different, we get the same thing here. We have the case that x squared was x was in the x direction was tangent to order 2. In the y direction it was tangent to order infinite, in fact. So there the trick was to change coordinates so that it became order 2 in both the x and y direction. So this is what one can try to do something similar for these ellipsoids. And just to now get back to the original calculation, because I want to stay very non-technical. Let's say you have this r is the defining function is u plus x to the 6 plus higher order in the y. And but so we don't have the right order of tangency in the y direction. So now we use a similar trick as we did already in degree 2. We in this case we take and add and subtract the real part of z to the 6 times a small constant, and then we calculate. First of all, you get that r becomes, you take the real part of w plus epsilon c to the 6. So that's this part. Then you have the x to the 6, and then you have the other term. And then you calculate it out, and then you get for this real part, you get just x to the 6 minus 4x square, well, something, 4x to the 4th y square, 4x square y 4th minus y to the 6th. But anyway, what happens is if you look at the coefficients for x to the 6, you have 1 minus epsilon as constant, which you can think will be almost 1. For y to the 6, you have still an epsilon, but unfortunately, you also have epsilon for the other 2 missing terms. You can throw out this because it's positive anyways. But it doesn't matter. The thing is that this is sort of like a small constant, large constant situation where this kind of term is dominated by a sum of the x squared. Well, sorry. Yeah, well, it's not exactly that, but it's a small constant, large constant argument. And if you do that, then you have to have a little bit worse for x to the 6. 82 epsilon, this is very crude. And then you get a little bit worse for the epsilon to the 6, but still it kills all the other terms. So therefore you get that r is larger than the real part of w prime plus a small constant times e to the 6. So, but some constant for which you have control. And so for the tangent plane at 0, r becomes larger than b times e to the 6 in all directions. So the hypersurface w prime equals 0 is good in that sense. Okay. And then you can write down, when we did this explicitly in this paper, we did some explicit calculations of what phi could be chosen to be. It doesn't matter too much because I'm not gonna go into that too much, except that if you have this formula, then you get good order of tangency in all directions at all points. So phi is tangent to optimal order at all points, and always in both in the real and imaginary direction. So then the question was to generalize this to convex domains of finite type. And there, instead of ellipsoids, they use general convex domains of finite type. And this, so for this was the reason we did these support surfaces was to really construct kernels to solve the bar. So it is, but that's not the focus in this talk. But nevertheless, the first result for the convex case was by Kumaj and Estime Lipschitz optimal dans le convex de type fini in 1997, encounter on the note. But the details appeared later. Sharp estimates for deep bar on convex domains of finite type. And later, we also proved the following. When I say later, it's published before her result, but after her announcement. So, and I think she had a manuscript in 1998. So never mind. She gets the she did it first. So but we proved Hölder estimates on convex domains of finite type with Fischer, student of Didrik at the time, and the reason I mentioned this now is because prior to this result, Didrik and I wrote a paper where we really only worried about the support functions and not the applications to the bar. The application to Henkin Ramirez integral reproducing formulas that could be done. Although we didn't write that, we were really only focuses on the support surfaces. So this basic ingredient phi. Okay. So let me say a little bit about that. What are the so you have a bounded convex domain with C infinity boundary of finite type in Cn, always D'Antlo type, and zeta is in the boundary. Then we make a coordinate change. So that zeta becomes the origin. And the domain is more like this in these new coordinates. And then the outer normal becomes the in some coordinate axis. In the real part, in the W1, the real part of W1 coordinate axis. Doesn't matter really, not going to care too much about formulas. So there's the domain lies now, it's a convex domain in this new linear coordinate change. So we take a unitary matrix for rotation and translate so that zeta goes to 0. So it's a very simple formula. At least you can do this locally in a neighborhood of a point on the boundary. And now you start with a smooth defining function for omega r, a rho. And it can be chosen to be convex. And then you get the defining function r zeta. Call it w less than 0 in these coordinates. And then you get formulas that depend on the parameter zeta and these new coordinates. So we have formulas for the functions, support functions, but they depend. The coordinate change is built in. So zeta varies with the point on the boundary. So therefore, it looks well. This is it's seen only here because you have the zeta appears there. But from this formula, you see it's sort of like normal. It is well. The key is to look at when W1 equals 0, really, and then these two first terms are 0, and it's the question of making these terms under control and positive. At least the real parts of those should be positive. And it is a very strange formula involving not only, let's say, type 2, that is second degree terms, and the highest order type of the domain, but all sorts of terms in between. So it's a little bit some procedure to find this formula. The constant m is very large. It appears in strange ways to different powers for the different j's. C is just some small enough constant, and then the sigma j's are just something which is basically 0 or 1 or -1 according to whatever. And then we get our phi by pulling back these. So phi of zeta z, which only be smoothly depending on zeta, but it will be holomorphic for each z in the z direction. Anyway, so this is a complicated formula. So why is it so complicated? And I just want to say a little bit, just a few words about why it should be so complicated, that's all. Because the formula contains terms of all orders up to the type. So let's say we go back to our example u plus x to the 6. So 0 is of type 6. The problem with the type is that it is an integer at every point, but so the type itself is a discontinuous function, but we want phis to be smooth. So we cannot have formulas that are jumping like crazy like that whenever the type changes. So we have to take into account that when you are near a point of type 6, the domain might be given as something nearby. It could have some second order term making it strongly pseudoconvex, but the epsilon goes to 0 when you approach the point. So in a neighborhood, you have to, the x to the 6 is in some sense a very important term for the geometry. but epsilon x squared is what determines the type. So you need formulas where phi varies nicely, and you can have worse stuff happening because the domain could easily, in addition, throw in intermediary terms like x to the fifth or whatever, where epsilon delta goes to 0 when you approach the point of type 6. So it means that in order to have smooth formulas, you really need to include all degrees in between the two, which is a strongly pseudoconvex case, and most points are strongly pseudoconvex case. The strongly pseudoconvex, by the way, almost all points are. So you have this problem all over the place. So this is just to explain why the above formula is so seemingly unnecessarily complicated. It has all these terms of all degrees included. Okay. And let me see. So this is the statement about from this paper then. So how large is this support surface? I mean, how far away from the boundary is the support surface? So this complicated expression says that there is an inequality that determines how large the real part of phi is. So let's say mu is a normal direction. Mu is a coordinate in a normal direction. So let's say we don't worry about that. We worry mainly about the complex tangent directions. And that is v is a complex tangent vector. Lambda is a parameter in the complex tangent direction. So this is what happens in the complex tangent direction. And you see that you have a complicated mess of terms, but they're all with absolute value. That's important. The term, you notice this formula has all these terms with messy stuff, but they also can point in all directions. They can be positive, negative, imaginary, anything. So, but in this formula, then what happens here is that these terms here appear only with absolute value in the right direction, namely negative. All of them are just so the absolute values are basically the same terms like higher order derivatives of the defining function, namely exactly those terms that appear here. There's those terms. Those terms. The absolute value of those terms appear when you do the estimates instead of the values which could be positive or negative. So how do you manage to get that? And then you have basically a question of getting rid of the sign of terms. And basically for convex functions in C. So we had a lemma, the main tool, to get rid of the sign and only have absolute values or coordinates of these derivatives. So Pj, you're looking at polynomials that are convex of the degree j, or homogeneous even, or homogeneous and convex, and of degree j. Then you have an epsilon j such that for any homogeneous convex polynomial, so we see here, the coefficients can be any sign or complex or whatever. But if epsilon is small enough, then if you add this term, which is basically only coming from the lowest order term, where the harmonic term, where there's no bar. If you add that, then you get something larger than basically absolute value of the coordinates of the coefficients. This one is not. This is not no problem, because you have terms like the real part of W plus this thing in here. So this becomes the new coordinate. So it doesn't matter that you have done that. But it says that PJ is with this addition is larger than something. Yeah, so it's a sort of a nice result for just homogeneous convex polynomials in C. And the lemma there was based on another lemma by a famous lemma, in fact, by Bruna, Nagel, and Weinger. They were working on the real line, so not on the disk, but on an interval. So we have, they talk about, yeah, so they talk about convex hypersurface, and they apply this lemma to things. But the crucial Bruna-Nagel-Weinger lemma is this. It's about convex function in one real variable. You take for positive integers m, which is the degree, and t is some length of some interval. Then you take all the real polynomials of degree m, or less than or equal to m, summation a jt to the j, and they vanish to second order at the origin. So it vanishes to second order. The first term is like t squared, and they are convex in the sense of the double derivative being non-negative. So in this family of convex polynomials, you have uniform estimates for all of those. And this is the Bruna-Nagel-Weinger lemma. And so there's a constant Cm here, which does not depend on the length of the interval. And it doesn't depend on which polynomial you use. Then P of t is larger than what you get by putting the absolute value of the coordinates. So here you have of the coefficients. So the AJs could be positive or negative, but here they appear only with absolute value. And this is the lemma in the one real variable, and we took advantage of that to be able to prove this for convex polynomials, which then would be convex of all real lines through zero, of course. So we can apply the lemma in all real directions, and then somehow put it together. So this is what I want to say about convex domains of finite type. Support surfaces for convex domains of finite type. Okay, so then I want to mention briefly there that there is something slightly more general than convex domain. It's called linearly convex or linear convex. I don't know, all sorts of notations. And various definitions. I use this one. Linearly convex domain. It just means that omega is smooth and bounded, but the domain doesn't have to be convex. So this was a bad picture. It could be linearly convex, meaning that you can take a point P in the boundary, and then the complex tangent plane. The complex tangent plane only. The real tangent plane is a disaster because it will cut into the domain. But the complex tangent plane, which is a complex codimensional one, could touch only at the point P. So to think of it, this is the complex tangent plane. It sort of manages to stay outside. The domain in this direction is more like that. So that's the idea of being linearly convex. And so since we are focused on complex support surfaces, that's not so bad, because the complex tangent planes gives you rise to function phi of zeta z as before, as for the convex case. And the question again now is the order of tangency, that might be terrible. And then one has to worry about that. There is a characterization of linearly convexity, which is more like a technical condition that we I don't know, I'll mention it since it's very crucial. By Bianchi and Peschel already in 1935, stor teori der funktionen mer komplexe föränderlich än konvexitet in betog av analytischen Ebenen in kleinen und großen. And they introduced some kind of holomorphic version of the Hessian, where you on the Levy form had DDCI, DDCJ bar, but this has only without bars, so half of the Hessian or something. And the Bianchi-Peschel condition is that linearly convexity can be characterized is equivalent to the real part of this complex version plus the Levy form being non-negative. And I should say they proved one of the directions. I mean, they didn't prove equivalence, they proved the implication in one direction or the other. I don't even remember which direction. But the other direction was done by Kieselman in 1998. So that this condition is not necessary and sufficient. And here you say it's called linear convexity and linearly convex. So I don't know what is correct. So we will assume also that the domains are of finite type. As always, well, we're given up on the infinite type. Then the conclusion in the convex case still holds. Namely, you have local smooth families of support surfaces given by phi of ZZ, somehow turned around these, I don't know why, which is holomorphic for each Z in the boundary. And the hypersurfaces touch the boundary according to the type of the point as for the convex case, meaning you had, in this case also, you have the same kind of estimate with these absolute values. That works there too. But it's a long calculation. I'm not going to go into that. But this is gives you Henkin Ramirez reproducing kernels. So, and we proved it in this paper, but we only worried about actually cooking up the holomorphic support surfaces. Later, oh, I don't even mention that. Did I do? I did. Oh, I didn't write this down, but there was a paper later by Diederik and his student Fischer, who worked with us on the convex case, that they also proved Hölder estimates for d-bar on linearly convex domains of finite type by using these support surfaces. Anyway, so, but it's not a topic. Now I want to talk about the reproducing kernels for the Koningberg domains in C2. What is the problem? The thing is, this is a sort of, call it a Henkin Ramirez reproducing kernel for Koningberg domains. So the Koningberg domains is not convex and not linearly convex. It's yeah, and it doesn't have these fees, right? Because any zero set of a fee would have to cut into the domain. But let me state the result that Wiegering and I got, namely, yeah, 88. So you have a continuous function. So we have a holomorphic reproducing kernel. That's the point. Yeah, you have a continuous function on the boundary. the FJs are some pieces of the boundary. The boundary is divided into some pieces, and FJ. So and for each piece you have a different kernel, but they are holomorphic in W. So you have these kernels, 3 kernels, and you start with any function continues on the boundary. Oh yeah, I should say omega r. Oh yeah, here. Oh. I didn't say what omega r is because the Convex example is unbounded. So omega r is just you intersect with a ball of radius r. And this is why you have 3 boundary pieces. You have one boundary piece, which is the original domain, one boundary piece for the ball, and then some corner stuff. So these are the 3 pieces of the boundary. And you have a holomorphic continuous function on the boundary, and it's holomorphic in W. So the integral becomes holomorphic on the domain. And if you happen to start with something which is holomorphic, if F happens to be holomorphic on a continuous on the closure, holomorphic on the inside, then it reproduces the function. You get the function back. So that's why it's a holomorphic reproducing kernel. And how to do this? Well, I'm not too much time left. It doesn't matter. It's just very technical. As I said, well, first of all, it's a Von-Nirenberg example. So you talk about the real part of W2 plus a homogeneous polynomial, and then some nonsense added term, doesn't matter. And the crucial part is that P of W, the bad points are that W1 equals 0. So when W1 is 0, there you don't have support surfaces. So when we talked about the boundary of omega, we only worried about that part where the first coordinate is non-zero, because it's hopeless at W1 equals 0. You don't have support surfaces. But for W1 different from 0, you have, you can imagine, in this case, we had the strongly pseudoconvex. You have local support surfaces in tiny neighborhoods. So it's a question of finding something extremely local in very tiny neighborhoods, shrinking when you go towards 0, and then get global solutions, global support surfaces, and still have some control so that it's not too terrible. So anyways, so I'm running out of time anyways. And the 3 kernels are just Luray, from some Luray maps. That's a standard way of cooking up integral representation formulas. So let me not go into that. And there's the horrible coordinate changes. So anyway, it works. So let me just stop with the concluding remarks. The thing is that the Henkin Ramirez kernel, reproducing kernel, was done for strongly pseudoconvex case. And now with this example of a Von-Nirenberg domain, you can make them for the Henkin, for the Von-Nirenberg examples. But it would be reasonable to ask that if you have an arbitrary finite type pseudoconvex domain in C2, does there exist a Henkin Ramirez reproducing kernel? And maybe wrong, he knows already the answer, but I don't know the answer. So can you have that for arbitrary finite type pseudoconvex domains in C2? It would be nice to know that. But also you have, of course, the question in higher dimension. Very little is known in higher dimension. So it seems to me what happened is that you can solve after solving the bar, which was done by Range and ourselves in a very small, simple case, finding the Henkin Ramirez reproducing kernel for the Von-Nirenberg example was I thought, was more difficult. So that is a curiosity maybe. Solve the bar, is it more easy than finding Henkin Ramirez reproducing kernels? Because historically it was the other way around. You did Henkin Ramirez kernels first as a building block for the bar. Anyway, so the bar, I'm out of time. So his history, Rang solved this for he solved the bar for the pseudoconvex domains of finite type in C2 already in 1990. And recently in this year or last year, Grontmeier, Simon, and Stensnes found supernorm estimates for the bar in C3. But there is the question of Henkin Ramirez reproducing kernels still is open. And there's another question about peak functions, which are also one wants to have when I study the pseudoconvexity. And I should say this was done with Bedford before solving the bar. It was easier than solving the bar. Peak functions were the easiest problem, easier than the bar, easier than Henkin Ramirez. But in higher dimension, the peak function problem may still remain unsolved in C3 and higher. So which one is the most difficult one? Is it the peak functions, the Henkin Ramirez reproducing kernels, the D-bar? So there's something, but anyway, so I'm out of time, so I'm stopped here. Thank you.
Thank you, Professor Fornæss. Does anybody has any question? Any questions? It seems to be that Araceli will want to ask something.
I am clapping.
Oh, sorry.
Oh, okay. Thank you, Araceli.
That's a clap.
Sorry, I just saw a very funny sign here.
Hi, John Erik.
Hi, Araceli.
So thank you, Professor. So we stop recording.
Thank you. Yeah.